Okay. Back to Spark. So we've got this world where we're writing Python and kind of being told the lie that Python is happening. But it turns out if we really wanted it to, Python can happen. So it's something like this. And this is like what I've actually written on the slide. You shouldn't do this as a user-defined function because I can just do that in Spark. But, you know, we'll leave that aside. This is, I guess it's most analogous to the numpy.vectorize, where you have a normal Python function that does normal Python work. Like probably, you know, imagine I'm importing some crazy Python module here, right? Like doing some calculation that I cannot do with this is normal Spark select kind of operations. And then I turn it into a function that can be called on a Spark column. I've got to say what the type is because Spark has to produce an execution plan, I guess, right? We've seen that enough. Spark had better know that, well, I'm going to put something into this function and what's going to come out is a bunch of integers because then it can allocate its memory and whatever. And then, well, I have a function that takes A and B as arguments. So I give it, instead of 2 values, I now give it 2 columns. Same as the vectorized NumPy deals. And what I get back is a column. It does a thing. It calls my Python function a million times on a million values or whatever. Well, I guess 10,000 in my example. Great. But we have this picture, right, where the code I'm writing is over here. The code that's running is over here. And we've got to get all the way across. And when I've said something like this, or frankly, anything we've done up to now in a Pandas Spark data frame, all of these values are not Python values. They're, well, I don't know what. They're Scala values or Java JVM internal representations or whatever they are. So there's this huge conversion process back and forth, right? I expected a Python integer. I returned a Python integer. Those had to get converted back and forth. That's going to suck, but it's going to work, right? If I have something here that I just can't get done any other way, well, I can get it done this way. Yeah, like, so this being a good example, like you've seen this happen, right? You've seen RGB to lab with scikit image or whatever. There's perfectly other good ways to do it. I don't think these are them though. Okay, maybe scikit image is a way to do this. But this is a whole image. Anyway, I'm sure somehow or another I can write a function that takes, like a Python function that takes R and G and B values and calls whatever library I can find and then returns L and A and B values. I'm sure, I could go to the Wikipedia page and I could figure out how to convert RGB colors to lab. And then I could implement that with data frame operations, you know, with great pain and suffering. Probably that would be faster, but boy, this is going to be a lot easier. It's a lot less of my time. Turns out you can do a little bit better than that. So that story are, what do they call them? Scalar UDFs or something, or Python UDFs. There's this, well, new air quotes, Pandas UDF option, where instead of this being one Python value, this is a column of a Pandas data frame. And I can do whatever Pandas stuff I want. So instead of doing Python stuff in the function, I do Pandas stuff in the function. It's actually a partition at a time. So like if you think of a partition of a Spark data frame as a Pandas data frame, you're wrong, but not like very wrong, like only technically wrong, not conceptually wrong. Maybe I'll say it that way. There's this beautiful thing that sits in between that's basically Both of these tools have agreed we will represent, well, a data frame from pandas or a partition from Spark the same way in memory. So it turns out you can just hand pandas that memory thing in some sort of shared memory situation and it just does it. We know that doing pandas operations is faster than doing Python operations in a loop. I think we know that. Well, if not, I have an example coming real soon. Probably there's still a little bit of overhead there, but let's compare. So I have made up this calculation for no good reason. It's just what fell out of my fingers when I was making the slides. I'm like, oh, I got two things I could do. A plus 2 times b times log of a. Why not? And this is what I should do, right? This is a all Spark all the time data frame operation, and the optimizer can get a hold of it and whatever. It's completely transparent to like Spark and the optimizer and everything, and that's great. This is the right way to do it. But what I could do, the next worst thing to do, is as a pandas UDF, and I've type annotated things here just so it's clear, but now I have a function that takes two arguments, a and b. These arguments are pandas series. So it's not the entire column of my Spark data frame, but it's probably the column of a single partition of my data frame. And then I can do, yes, that gives it away. I can do some NumPy or pandas kind of operations on it and return a new column. I'm sure there's some rule that says, you know, all three of the columns implied here have to have the same elements, right? Because I'm doing a presumably select operation. Or I can do the pure Python UDF where this is called, I guess maybe I'll say it this way. This function is called once per partition. This function is called once per row. I think that should be slower. I have to really do these type conversions. I have to call this function many, many more times. It's closer than I would have thought, at least on this data on that day with that Spark and Pandas version. Right, I guess, yes. The other thing I could do is move over to the Scala Java JVM world. I don't want to do that. That sounds horrible. This is pretty minimal. Like I think other, like that blog post that was linked a few slides ago, like I think they get a like 100x speed up type of thing. I can never, this is way too long. I can never actually find the important part of it. Or maybe it's a different blog post. Okay, so I got a like 3.5 times speed penalty for doing it the dumb way. That's still not nothing. Again, that seems to be about the smallest you can expect. So I think the lesson here is UDFs are there if you have no other choice. Sometimes you don't, but try to stay in Spark world if possible. Okay. SQL has been creeping in, right? I find myself, like I said a couple times here, hey, by the way, if you know SQL and you've done database queries, that might feel familiar, or we might be about to do something in Spark that feels familiar to you. So Spark is definitely not a relational database, but it just, the ideas just keep following us around. One of the reasons is SQL is a really useful way to express the kinds of things that people do to data. I had to look this up. Happy 40th birthday SQL. And this is still like the absolute first class thing, right? Like if you want to manipulate data, the SQL query language, which I guess if you don't know is the query language for databases. Like if you're going to talk to Postgres or MySQL or Microsoft SQL Server or SQLite, you're going to speak SQL to them. It's the way you express these kinds of thoughts, right? The thoughts like this that we're expressing here with Spark method calls end up being expressed as SQL queries. And then we start writing Spark, and okay, this is just import here called .sql, and UDF is a term, or select and filter and where and group by. These are all terms that you might know from databases. Yeah, if this is what we need to do with data, it kind of makes sense. There's also 40 years of work done on optimizing SQL queries. You know, when you write, you know, select this, join that, where this, group by that in SQL, there's lots of work that's been done by very clever people about how to turn that into a good execution plan and get the right results quickly. Well, since Spark operations kind of mirror SQL operations, the nice Spark people can use that, and that's great. It also turns out like Spark is just trying to, oh, sorry, SQL is just trying to kind of hard to get away from, I guess. I like this quote. This blog post is about something completely different, but yeah, it's just the details just keep following us around because it turns out it's really useful. And actually, I was just looking at this, and what? Oh, relational set theory. Sorry. Sorry. So I just like I realized in the next paragraph, once you add group by filter and join, you can no longer claim to have invented a new query language, just a new dialect of SQL with worse syntax. And maybe that's what's happened. Like maybe like if you're a lover of SQL queries and SQL databases, maybe you look at Spark and think, oh, this is a database but worse. So it's not a database, but maybe it's worse than SQL. It turns out if you feel that way, you can say it that way. So this Spark.SQL function basically takes a string that represents a SQL query and does it on a data frame. So I guess I do have to register here. Like I have a data frame back in Python land. I just have to say this data I want to refer to by this name. And then, well, then the name works, right? Like this string does refer to that data. And then I can express myself with a SQL query on a Spark data frame. Or I could express myself with Spark method calls on a Spark data frame. What's going to happen is I build the exact same execution plan either way. So I really have a question of style here. Do I like this? Do I like this? And in some ways, I think this is unfair because for code that's small enough to fit on a slide, I think the SQL representation of it is probably simpler because it's good at that. I don't know if any of you have had the misfortune to have to write or especially debug or modify a SQL query that's like 10 lines long in your text editor. If you have had to do that, you did not have a good afternoon. I think I can say that with confidence. This, of course, I can write it. In fact, even this, I don't even like the way I've written it on the slide. Because, of course, what I can do in let's go. I could write it this way, or I could say, I could just do this. Even if I just break the calculation up into steps and then use good variable names, it's so much better. Whatever, like obviously I have a fake calculation here, but it's just so much better to have these variable names and to use that as documentation. And of course I could include a comment in the middle of it. And if I have a 10-line long SQL query, I can't do any of that and it sucks. But for the moment, the operative observation is I got the same execution plan, whichever way I express myself. Or it turns out you can use some like fragments of SQL queries in the right spot, and maybe I like that better. I get the same execution plan that way as well. Yeah, again, question of style, fundamentally. The reason I haven't brought it up until now is I do want you to see the method call syntax, the method call style. I think, again, it's usually better for anything bigger than one slide. But again, it depends. A little bit of question of style. I'm certainly never going to ask you to write a SQL query for this course, but FYI. It turns out everything we've just talked about is only half of Spark. So this Spark data frames business is great. It's probably the way like 90+% of Spark work is done in the modern world is with data frames and data frame methods. Because of course it maps pretty nicely onto the ideas from SQL, and we like those ideas and everything else, but it's just not always enough, or not always a really good fit, depending on the kind of calculations you're imagining here. The other thing, the other like tool we have is the RDD, Resilient Distributed Data Set. And I feel like this acronym, like it both makes sense and doesn't. I think data set, sure. Distributed, sure. Yeah, right. You know, we have a compute cluster and parts of our data are in different spots because different workers are working on different partitions. Resilient in the sense that I guess we saw with the execution plan that every data frame knows its entire history. And one of the implications there is that if we have a compute cluster and one of the, we have 100 compute nodes and one of them disappears because network failure or hard drive failure or who knows what, it's possible to recalculate whatever it had. Like whatever partial results it had can be recovered. Like you can take those partitions and pass them over to some other node and have them recomputed. It's going to be slower, but resilient in the sense that we're a little bit fault tolerant at least. Anyway, and this is also true of Spark data frames. An RDD is like, frankly, in my mind, it's a list. It's a Python list. And in that way that you can say in a Python list, I can put anything I want here, but maybe I choose strings today. I could mix, but I'm probably not a psychopath and won't. So this is what I mean by like a one-dimensional data structure. This is the kind of thing I can also put in an RDD, but probably bigger and distributed, partitioned. So it's a lie to say that a Spark data frame is a collection of row objects, but maybe it's a useful lie. Like maybe this is like if you look at a Spark data frame and think, okay, what I have is a bunch of rows and those rows are partitioned up. Oh, then it's kind of just like an RDD of row objects. Super very much a lie, but you can be told that lie. If you have a data frame, one of the things you can ask for is an RDD of rows. Wow, that's a super not very interesting example. But yeah, you can say dataframe.rdd and get back an RDD of, it turns out, row objects. Here's a much less silly example. So I have the data frame that I think was the first data frame we used in Spark a few weeks ago. When we did a .show, it looked like that, and great. So if I say that .rdd, that gives me the underlying RDD object. It turns out RDD objects have a take method that gives me the first n rows of it. And what I get was this. So now I have a data structure that has 5 rows represented this way. I think it's pretty obvious what that representation is. Like this seems pretty reasonable. Also partitioned, right? So I might have, if I have 5 billion rows in my data set, I've got a bunch of different partitions on different computers, and that's true after I say .rdd as well. So, one partition has these rows in it on one computer, the next partition has these rows in it on another computer. That's also true in RDDs. But what's happening now is as soon as I switch to an RDD, I have Python objects. So in a data frame in Spark, Spark knew what all the values were, it knew what all the types were, it was managing that we have all of these columns, and that was kind of mostly to our benefit. But now what I have is, frankly, Spark has no idea. Spark is just like, hey, you got a Python object there, good job. I'll move that Python object around in whatever way you want. It doesn't know what's going on. It's just a Python object that's been turned into bytes somehow. Like if it has to move across the network, Spark will run it through this tool that will turn Python objects into bytes, move it over the network, and then unpickle it. Sorry, the thing that I hate, this kind of thing is so annoying to me. Like, this is just, okay, I want to take my thing and I want to turn it into bytes, and then I'm going to send my friend those bytes, or I'm going to have my web server produce those bytes, you know, whatever. This is totally normal. And the fact that it's not secure, even though it feels like it should be, like it feels like if I'm going to turn these objects into bytes, I should be able to send those bytes over the network. God, I hate, like, if you have to have this big flashing warning, maybe you've chosen your defaults wrong. Maybe there should be a pickle, you know, unsafe equals true option you can turn on if you know what you're doing, but the default should be safer. Anyway, nobody asked me. Okay. So if I'm going to work with an RDD, yeah, I'm going to be doing more Python work because I just have a bunch of Python objects. Again, effectively just something that I think of as a Python list, but I kind of also know in the back of my head is distributed and in a compute cluster. But I can do something like this. So this is the older Spark context as opposed to the new Spark session object that we've been working with. I can say, hey, read these text files, or this one text file, into an RDD, this other data structure. When I read a text file, what I'm going to get is a collection of strings. So Spark has no idea that there's like a comma here, right? It's just like, okay, I found 6 lines in a file. I gave you an RDD with 6 strings. So here you go. But then I can do Python-y stuff with it. I can like do a map. And map now means, well, it's like apply or like a vectorized kind of operation. This is one Python string. This is one Python calculation that produces one Python string, I guess. I'm mapping a string to a string. Okay, fine. And then filter, well, whatever filter is, it better be a function that returns a Boolean, because it's, you know, true means keep it, false means throw it away. But I can take whatever values I want. Again, whatever one record is in my collection, take one of those records and do this with it, return true or false. Okay, and I what have I done here? I have, the only thing, okay, I'm throwing away this one row, right? So I've realized, oh, this one row, that's my header row. That's not real. I didn't want it. So I can filter it out, sure. There's realistically not much you're going to do with an RDD. If anything, it's probably like, probably mapping and filtering is it. Realistically, what I would do if I was having to deal with an RDD, and the reason to work with an RDD is you get the flexibility of being able to do like arbitrary Python stuff. Once in a while, that's really useful. And I would do as little as possible and then convert it to a data frame, frankly. But maybe I want to throw away some data. So I want to look at the records that I got from wherever I got them, and I want to keep only certain things based on some Python function. Or I want to write some Python function that takes one of them, does some stuff, gives me a more structured result back, and then move towards a data frame realistically. Yeah, the methods are different because they're totally different data structures, right? A data frame has rows and columns and structure, all of the structure and everything. An RDD is just Python objects, so we have to deal with them differently. Of course we do. When we're in RDDs, we're going to be doing Python stuff. The work is not being done by this other tool. Maybe that makes us feel good because we have more control. We can be a little more precise with our manipulation, but probably it's going to be slower. Probably. Yeah, we don't, and especially we don't get the optimizer. Like looking at this code, like what Spark knows is here's a Python function. It has no insight into like what's going on in here. So it can't optimize. Like there's no way for it to optimize like, oh, I'll only read these bytes from a file or whatever. I don't have to read these because they'll be filtered out. No way it could possibly know that. It just does the thing. It also means that like when I said back here, oh, you can just like take a data frame and say .rdd and get the RDD of rows. It looks like that's just like accessing a property that's already there, and it's really not. It's think of it as an actually quite expensive method call. But here's why I haven't deleted this section in the slide deck. And every time like I've said this before in this class, every time I see and I'm like, RDDs, do you really need RDDs? I don't know. Okay, it didn't happen this semester, but it does seem like definitely the last time. Happens like clockwork very often. I have that thought, and then somewhere in between having the thought and actually giving this lecture, I have to use RDDs for something. Again, it didn't happen this semester, but it does seem to happen weirdly often. Apparently there's something about week 11 or whatever that makes me use RDDs. Okay, so let's say I have this. Like, I've been handed the data file. I don't have any control over it. I just got to deal with this. And I probably could deal with this as data frame operations. I could say, like, you can read text files in a like spark.read.text kind of way and get a data frame back. And the data frame is like each line in the file turns into a string, and then you just have one column of all those. Okay, so I could probably go through the Spark functions, string manipulation tools, and figure out how to work with them and do the thing. But you know what's easier? It's just a stupid string. I can just write some Python code. That would actually be totally fine. Turn the RDD of just each line from the file into an RDD with a bunch of rows. Then I can turn that into a data frame and carry on with my life. Once in a while, that's easier. So, because I just have access to the python.split function, I can just deal with it. I can do the data type conversions. I can do these for sure. I can do these in data frame operations, but I just know how to spell this. I can get it written really fast and then read the text file into an RDD. So an RDD full of strings, one line per string. Do this to each one. So now I still have an RDD, but it's an RDD of these row objects. And that's something I can do exactly this with. Then I have a data frame. Then I can carry on with my life. I can think of this. I could even call this ETL if I want to sound fancy. Do this work to make my data less stupid. Then I can just get on with it. Whatever calculation I'm imagining happening next. I could have, I guess, yeah, I could have written a UDF. Well, if I'm going to do the work in Python, why don't I just do the work in Python? I guess is the thought I would probably have here. Once again, an RDD is partitioned. The way I've written it here kind of implies I'm going to have one partition. Maybe not. Like, I would probably like more than one. Like, and I have done this for like stupid file format, but like each line in the file was an XML fragment. And it turned out just the easiest way to deal with this was to call a Python XML library to turn it into a data structure, pick the parts I care about out of that data structure, and then return a row and get on with it. Maybe getting on with it is just writing it to disk and then saying, oh, here's step one in my data pipeline, ETL. Sure. I want to point this out because there's this distinction of like, how do I represent data? And inherently RDDs have to be row oriented because, well, they're one dimensional. So if I want to have like more than one thing that I think of as a column, it just has to be part of this object. So therefore, what's being stored like adjacent in memory are rows, which is what I mean by row oriented. Did we see, or did I just say, but pandas is columnar or column oriented, which means that, again, the collection of things, like if you look at what pandas has in memory, what's sort of all together is a column. So if I have like, what was it, count or whatever was back here, count and measure, sure. If I have the column count in pandas, that would turn into an array of integers, and that measure would turn into an array of floating point values. Not, I have a row that is the country and the count and the measure, which is good because the row-oriented layout is wrong. in the modern world, I don't think I have any defense for row-oriented storage other than maybe it's really convenient sometimes for the programmer. Basically, if you're in 295, all that stuff is why you don't want row-oriented storage. I need my columns to be together because that's how I'm going to operate on the data. It's going to make these vector instructions accessible to me. It's going to have better, everything is better. And so this is why Spark data frames are much more column oriented. And this is, like I said, that you could think of a Spark data frame as an RDD of rows, and that's a lie. And that's a total lie. The basic memory arrangement is different. If you want to think of a Spark data frame as a collection of pandas data frames that we just happen to now call partitions, that's also not true, but it's super close to being true. It's why these pandas UDFs are fast, right? So in the Python UDF, where it's each, or like call this function once for each row, okay, I have to have a Python object, convert to Python object. The pandas UDF, where this is call it once for each partition, it turns out this is pretty cheap because what Spark has in memory for each partition is very close to a pandas data frame. So calling this and handing it what is effectively a column of a pandas data frame, super easy, super fast, because that data is basically already waiting for us. So I don't know, again, if you want to think of a Spark data frame as a collection of rows, the Spark police are not going to arrest you. Like, keep in the back of your mind somewhere that you're lying to yourself. If you think it's a useful lie, then fine. I'm just telling you, each partition is a pandas data frame is much less of a lie, much closer to what's really going on. So this, I think, has implications to like what if we want to move back and forth? And what I mean here by like only Spark is that there was never any like, arguably except for the pandas UDF, there was never any like permeable membrane there. It was always like our data was in Spark or it wasn't in Spark. There was no moving it back and forth between the Python code and the Spark code. Yeah, usually that's good, right? And I've seen people do this. It's often something like, how do you do this in Spark? And what they'll find is a way to do it in pandas, or what the LLM will crap out is a way to do it in pandas. And then it's like, okay, well, how do I get the Spark data frame to be a pandas data frame? And then everything breaks because pandas data frames are in memory and you're in trouble. But hey, not always. Sometimes not. And I think maybe it makes sense to think about the two directions separately. Sometimes you have a small data set that you want to move towards Spark. And maybe it's because I want to do a join, right? I have my lookup table or my keys or my type index or whatever it is. And I want to do a join, and hey, it's probably going to be a broadcast join because I have a small side and a big side. Well, if I'm going to do that, I need it to be a Spark data frame before I get there. Or in the other direction, again, if I'm going to do a group by, like I'm going to put a word here, or more than one maybe. And if I group by a column, what I have left is one row for each unique value in that column. Hopefully, if I have some idea how many those are, maybe it's a small number, and then why am I using Spark anymore? I have small data. Why don't maybe the next thing I'm about to do would be easier, and I'll just do it in pandas. Totally reasonable. Well, I guess maybe this is by far the most useful thing I can say here is there's a Spark create data frame function. One of the things you can put there is a pandas data frame. Then you will get a Spark data frame with one partition and all of that data. That is the super easy way to, like, there's a super easy conversion. It's a super obvious conversion. Like, obviously the shape of everything, like I have rows and columns, and the columns have names and the columns have type. This is the same. It's true on either side of this conversion. So should be nice and obvious and easy. Or yeah, other like two-dimensional thing, like anything that's kind of the right shape. You you can say here. If you're giving untyped data here, you probably have to specify a schema, which we have done. I guess we're doing it when we're like reading CSV files, but this is just like Spark has to know the names of the columns and the types of the columns, which are not specified here. Probably I should give a more concrete schema. But well, you know, whatever kind of thing you've got. I get one of the things I did mention there is a few minutes ago, so I can say create data frame and give it a pandas data frame. I can also give it a bigger data set as an RDD of row objects. Also a perfectly good way to build a Spark data frame. In the other direction, if I know my data isn't too big, I can just say .2pandas. That will turn a Spark data frame into a pandas data frame in the driver. So if I'm done with this, like if I just say .2pandas without thinking about it, okay, like totally reasonable for a Spark data frame to be a terabyte of data. It's totally unreasonable for a pandas data frame to be a terabyte of data. So I really want to be mindful with this function call, but okay, fine. The other thing you can do, .collect, is give me back a Python list of row objects. If you're going to be doing something really, you know, Python-y, I guess, but probably this one is the more useful one. Give me a pandas thing. I know how to work with pandas. So again, this, if you say .2pandas and there's not a comment nearby that says why you have determined very carefully with thought and insight that this is a safe thing to do, you have written incorrect code in my mind. This is super sketchy if you don't think about it, right? If you think about it, you're like, oh, you know what I've realized? And like, I've certainly written code where it's like there's one row left. You know, if you do a group by with nothing in there, you're aggregating all the rows into one. Sometimes that's what you want to do. I want the total, the sum of everything or whatever. Yeah, then you can say .collect. Yeah, you can definitely fit one row in memory in your Python driver process, but you have to have that thought first. Some other ways to get data sort of to and fro, in and out of Spark. What we've been mostly doing most of the time is spark.read, spark.write on the data, like the file formats that we're like super comfortable with, right? Like the things I've given you for the assignments, I think they've all-ish been directory of JSON, new line delimited JSON files. Sure, and that's perfectly good data format. It's easy to understand. It's pretty like different tools all understand it, right? You can open with pandas, you can open with Spark, you can open with whatever else, and that's great. Both of these things, either in the RDD style or in the data frame style, are read a bunch of text files, and each line in that collection of files becomes a row in the data set. Again, either RDD or data frame. Or yeah, the things I just talked about, right? The spark.create data frame or the data frame.2pandas. Also ways to sort of get data in and out of Spark depending what you're doing. There's a few others built in. Spark.read. God, it's always so annoying to find this. It's not. Is it under input and output? Oh right, it's so. Spark.read is a data frame reader object. Spark.write is a data frame writer object. So yeah, those have a CSV method or function, whichever word. Yeah, function. Okay, there's other stuff in here. Is what I'm talking about here. Just a Java database connector. That if you know how to tell Java to connect to a particular database, you could probably do that here with, again, the URL that you care about, and you say, okay, I want to talk about this column in the database, or sorry, this table in the database as if it's a Spark data frame. And actually specifically, I want only these columns. I don't know if you're going to come across org files, probably not. Although I guess I predict that one or a couple of you are going to find some data set distributed as org files for your project. They're out there. They're not super common anymore. Parquet files maybe a little more common. Most people who distribute big data sets seem to have decided new line delimited JSON is the way to go. It's the least painful, more flexible. There's other stuff out there. I keep not being sure if I need to delete this link or not, because the Spark packages, it definitely exists, but it has things like this library that is more than 10 years old and hasn't been updated and probably doesn't work in modern Spark versions. Maybe I should delete that link. Probably the data format that you should remember exists, and I think I've mentioned this before this semester, Parquet. Yes, because I'm pretty sure I remember harping on about it's pronounced parquet as a French word. It is, let's see, what is it? It's an open source column-oriented data file format. Okay, column-oriented, that means good. For efficient data storage and retrieval. Okay, well, hey, that's great, right? Because I have column-oriented data. I call it data frames. And I would like my data storage and retrieval to be efficient. That sounds great. And it is something Spark can read and write. It's something pandas can read and write in reasonably recent versions anyway. So, okay, reader and writer. Okay. Once again, I'm going to get the directory of many files. What this is really efficient and not text, right? So if I can open a CSV or JSON file, I can double click it or open a text editor or whatever. And that's not true for Parquet, which is bad because it's harder to inspect. It's better because it's just more efficient. It's designed for computers, not for me and my squishy human brain. I think, how about that? If you're thinking about Spark for the project, here's what I think should happen. You should be starting with a big data set, which you can, but you don't have to. You can just not, of course, in the project. But I would think of Spark as an ETL, extract, transform, load. So I have the data set, the big data set that I started with. I want to get into it, read it as a Spark data frame or whatever. I want to take the subset that I care about that's hopefully quite small. Maybe I can convince myself it's okay to do a coalesce one, so it's only in one partition after that. And then I want to write that out to Parquet files, or if I'm going to stay in Spark, leave it partitioned, be a bunch of Parquet files, because then I know that the next thing I'm going to do is going to be fast, and I like that. We've usually been compressing our data as we do it. In fact, I wanted to look at, oh, sorry, there's a compression argument here, and what I don't know is the default. And apparently I'm not going to be told the default. Oh, really? Data source options, yep. Okay. The default compression is snappy. That's a good choice. But that's definitely not true for CSVs and JSON. Anyway, I'm pretty sure this is going to be the case for when I write a Parquet file. The thing that's going to happen is it's going to end up being compressed with this very fast, not great in terms of file size, but very fast in terms of processor time compression. So if there's a lot of redundancy in my data, it will shrink on disk because there's some data compression, and that's probably good. I've usually been giving you, if it's been compressed, it's been gzip compressed because it works. You have, every Python install has a gzip library. Not every Python install has a snappy library, so I'm not quite sure. Again, I'm suspicious of that default. Let's put it this way. These compression algorithms they're fast enough that they are the default when Spark shuffles data. It's faster to snappy compress or LZ4 compress data and then send it over the network and then uncompress it than it is to send it raw over the network. A couple weeks ago, I asked about this for things on disk, and it's smaller files are faster to read because disks are slow, and very often the trade-off is worth it because processors are fast. This isn't going to be true for every computer comma compression pair, but often this is true to the extent that it's the default for a shuffle operation. If you sort or whatever, Spark will LZ4 compress by default, then ship over the network because it's just so fast to do that. Anyway, and you know, big data sets are big. Save some disk space when you're writing. Okay. I said this before, right? This is my descriptive definition. This is what people mean when they say they have big data. And let me expand on that. Again, just things like I have to think about the compression algorithm when I write my files to disk, or I have to think about the data format and its relative efficiency when I write my intermediate results to disk. And I maybe choose snappy compression and Parquet file format as a good default, but why do I care? Well, this is, these numbers are old. That number is now smaller than the truth. And I think I have a better SSD in my desktop at work now than I did at the time, but stay with me. You know, these are real numbers, right? Like this is not nothing. This is just, I want to read the data set off the disk. If it's on a spinning disk, which it might be on a big data set, I just have to plan ahead. I can't just say, oh yeah, read it and off we go. I've now got a commitment to just reading the data is going to take some time. If it's bzip2 compressed, which some of them are, the newer Reddit, I think, is ZSD compressed, or maybe they changed to something else again. But bzip2 compression is great in terms of file size. It's super, super annoying in terms of compression and decompression speed. Well, okay, if I was paying for the bandwidth, yeah, I'd probably choose the better compression. Again, moving this data around, it's a commitment. It's like you have to plan ahead, you have to know what you're doing, and these are not that big a data set. This is why, I guess it's why we have a compute cluster. And yeah, this stuff really starts to be a problem. Well, let me tell you, I'm trying to right now move this Reddit data like comment corpus from the compute cluster you're using to the one that we'll be replacing it with, and geez, what a pain in the butt, because it turns out they're on the same, both clusters are on those same really slow network switch, and it's being a problem. It's not a fast network switch either. We're down here. So depending where your data is, depending how it's formatted, depending whatever, you have different, like really different ideas about, you know, how fast it is. If you have LZ4 compressed data on a local SSD or over 10 gig Ethernet, you're going to get that data really, really fast. If you have a slow network share and gzip compressed data, you're using a lot of network and a lot of compute power just to get to the bytes you care about. These choices are really problematic. Let's put it that way. And also, how much disk space can you commit to the problem? So this is why we have a compute cluster, because you can parallelize a lot of these things. It's why, like, my advice, like, if you do want to look at that Reddit data for your project, you need to have a plan, you need to be careful. And I think since I'm out of time, that will be a good spot to stop, and we'll pick back up next week, have some more big data fun, and really enter the end game. So there's more than 1 week of material left, but a little bit less than 2, which is good because I think I have 2 weeks left now. See you on Friday. See you next week in lecture.